All right. Welcome everybody to today's VDAO Community Voices event. We are joined by Steve Boniwell of PSKL, Will Masters of Ogallala Life, and Michelle Avis of Fifth World and some other ventures that she's been a part of as well. And I'm sure she'll dive into those as well. But yeah, I mean, I can't possibly do a better job of introducing y'all than you all can. So please, Michelle, we'll start off with you.
Okay. My name's Michelle. I'm one of the co-founders of a permaculture education company called Verge, which has kind of morphed into Fifth World. And I'll speak specifically to kind of my involvement with water. Always been keenly interested in water. And back in 2014, thought I think I want to write a book on rainwater harvesting, somewhat randomly, but figured I could do the research and figure it out. And through that process, met an amazing mentor in Australia, Dr. Peter Coombs. And so I've spent the last 10 years working really closely with him on all things rainwater harvesting. So that's really the area of my passion and now expertise. Yeah.
This will we kick it off over to Steve.
Hi, I'm Steve. I'm co-founder of PSKL Water for All. I've got a landscaping earthworks background and yeah, excited to be a part of VDAO, and there's very exciting things going to happen, I can tell.
And that leaves us with Will. Go ahead, Will.
Hey, I'm Will. I'm an attorney. Well, I'm like an American. I guess I'm privileged to be connected to place. I live in the Southern High Plains in Texas Panhandle, and my family's been here, I guess, since the Great Depression. And my wife's family's been here since it's like really 1900s. And again, like my dad, I grew up, he took us to different parts of regions, hunt, fish, kick around. And so, like, it's really privileged to access this largely private landscape. And I just can't watch it. Like, it's just, I don't know, like Aldo Leopold's, I think he said, like, one of the dangers of an ecological education is just everywhere you look, that sucks. And that is certainly true here. Yeah, just a few years ago, I really kind of grew to despair. I'm sorry. It's wind. I'm as slow as I can. The law for solutions, and that's kind of when we got into refi. So, and I am sorry about that. I'll go try to find it. That's really spot.
Yeah, no worries. I know it's a bit of a wind out there. So most of our community voices are done with a bit of a short form presentation on the specific topic, and then we kind of open things up to a more community-wide discussion about that said topic. Will, if you're able and the wind isn't too bad out there, why don't you go ahead and kick us off with the first one?
Yeah, cool. So we do work in rangelands, very much like the one I'm walking in. And so it's a semi-arid landscape. It's used for livestock production. You see a lot of bare soils. We get a lot of erosion and cutting. And this is a draw. And in fact, there used to be some springs here that flowed from the base of the Ogallala. We've been building leaky weirs. This is one that we haven't built it yet, but we've got the material stockpiles. And so just like a low rock dam that crosses the draw. And whenever it rains, we don't try to stop the rain. We don't want to store it on the surface. We want to stop the sediments and kind of rebuild the alluvium. And you just soak as much of the stormwater as we can. And so 2 years ago, we built like 110 natural infrastructure and dry land streams, basically like leaky weirs, check dams, on a private ranch, this one elsewhere. And then it was awesome, but the public didn't seem to care. And we talked about it and thought about it. And I think it's obvious. The public isn't allowed to access it. Like, this is private land, right? So why is the public going to give a shit? Problem is, our entire landscape is privately owned. We found a piece of property. It's called Wildcat Bluff Discovery Center, and it is publicly accessible. So this year we built 80 kind of larger structures on it for floodwater harvesting, and we're really excited about it. The public is just, we've gotten a huge amount of attention. Last volunteer day, we had like 40 volunteers showed up, which is really big. And it's crazy, but we're like the only people doing this in this like vast geographical area. I mean, we're not the only people doing it, but we're, well, yeah, there's not any other kind of large scale projects, and we need to be a lot larger scale to succeed. So kind of our current challenge or problem is, how do we scale this type of approach? Like, it's inexpensive, it's low tech, it's safe to fail, but why would people do it? You know, even for all that, why would people do it? And that's a trick. And that's really, I think, why, or like what we want out of refi are better incentives. Yeah. So in like the outcomes that we expect. So our structures are like, they're temporary. And so you build a leaky weir, it fills up with alluvium, it degrades. And so in a few years, like we don't want to have a dam anymore. It's kind of like a ledge, it's level. But the biggest outcome we're looking for is increased biomass. And so we need perennial vegetation in our bottoms. And so the purpose of the structures is to act like a sponge for stormwater, and hold that water and nutrients long enough for riparian vegetation to come up. Once the riparian vegetation comes up, it starts to kind of self-perpetuate and strengthen itself. And so it's like kind of those natural systems, taking advantage of the natural systems. And it's been awesome. We've got a pretty big team. We've got about a half dozen that are involved day-to-day conversation. We've got a prototype, like a foam space mesh network, and that's actually why I'm out here today, is we're messing with this radio. We got like 4 radio nodes and a mobile node, and you can plug it into a sensor or your computer. You can upload data, and it's accompanied by metadata, which proves its location in a GPS independent way. And so you can just like determine like this data was reported at this time by this person at this location, and be absolutely confident that the location reporting is accurate, which is a pretty big deal. The foam space team's really interesting, and they're interested in MRV. And I kind of suggest that that's the crux of all of this, you know, and so there's various ways, like various structures of implementing market-based solutions, you know, like as bounties or as ecological contracts or as infrastructure. But it all comes down to, how do you measure, report, and verify like what happens and what gets done. And the only way to do that is to empower locals. I mean, it's silly to pay an engineer to travel from like Dallas or Denver to come take some soil samples. Like, no, we need people that live in the landscape, empowered and like kind of citizen science. And so we really like, I don't know, like DSI is an awesome thing too. Although I kind of hate the term DSI because it like shouldn't be distinguished from refi. You know, it's like all of these, it's like we're talking about using kind of technological advances, like they're multidisciplinary. And it's, like applications are useful in science and in governance and in markets and in finance, natural capital accounting, et cetera. We've seen, like, when we started to see carbon contract buyers, like developers, probably 4 or 5 years ago, at first we were really excited, like, hey, here's some money to pay for some regen projects. We got to take a look at the contracts, and there are so many flaws, MRV being one of them, but by no means the only one. And that, again, kind of spurred like us to form the nonprofit Ogallala Life and start working. But the reason I mentioned the carbon credit, like one of the other really fundamental problems is, if you don't have water, you're not going to grow biomass. You're not going to like effectively sequester carbon. And so I suggest that like land should be managed in a water-centric fashion in the dry lands. And you're going to get better carbon outcomes if you do that than if you manage it in a carbon-centric fashion. And so we're just really kind of trying to promote this narrative and figure out how to use the technology in a way that's suitable for our bioregional landscape and culture. And at the same time, we're trying to demonstrate to our bioregion that like these landscape rehydration work and are effective. And like people, we can say it all day long, but people need to see it for themselves. We've done work primarily in stream beds so far. We've got some infiltration earthworks that we're going to start on next growing season, and we want to do some like swales, keyline design. And then we also really want to do some work in what's called like a playa wetland, these like broad depressional wetlands. And that work would be inspired by like various like wetland agroecological, like traditional ecologic knowledge systems, like the Chinampas of Lake Texcoco, or like the Fundi of like Lake Loktak in northern India. There's just these really neat ways that people have lived in and with wetlands for a long time. And so instead of killing our wetlands, we should turn them into a garden. Cool.
Amazing.
And I hope, I hope that wind noise wasn't too bad. I am sorry for that.
No, it went way down, and you came through loud and clear. And it's a extra treat that you're actually out there in land, doing work while you're also, taking the time to come here. So that's awesome. We'll go ahead and move on to the next one with Steve. Why don't you go ahead and kick us out? I have a lot of questions for you, Will, but we'll get to that here soon enough.
How's that, folks?
Looks
All
good.
Cool. So I'm Steve, co-founder of PSKL Water for All. We're an Australian land regeneration startup company, and we're innovating in the space of combining unpowered technology to accelerate ecosystems. And that has some really exciting multiplying and compounding benefits for rapid rehydration and regeneration. And it's a quick way to get from degraded to regenerated. Today, I wanted to touch on some macro themes and talk about some of the challenges we face that aren't in the climate discourse. And then I want to talk about how unpowered technology on landscapes has really exciting potential for the climate moderation and for energy production. So as a generalization, I see three categories: green growth, the green transition, which is renewables replacing fossil fuels in our energy hungry lives. There's just sort of we get to keep going as we are. Degrowth, which is an energy descent future, and regrowth. So that's sort of within the regenerative paradigm that Michelle and Rob talk about. And it's about self-replicating living systems. This is where we see the massive untapped potential, especially when working with unpowered technology. So in the public discourse, there's a lot of things that aren't talked about, and yet there's a huge amount of energy, resources, and intellect going into renewables. Nate Hagens of the Great Simplification podcast talks about renewables more accurately being called rebuildable, and that's if they're engineered and manufactured to be rebuilt and recycled in a cost-effective manner. Currently, only about 30% are, and I'm sure we've all seen images of renewables going into landfill. So it's not a particularly well thought out plan. Simon Michaud is a mining geometallurgist, and his research concluded there wasn't enough key minerals for the first generation of a global electrified fleet. So it's just further emphasizing renewables are important. They're already a significant part of the energy mix and the climate drawdown mix of carbon. But it's really important to be strategic. Degrowth, making do with less, I think that would likely play out to an extent, but I don't think that those in the degrowth paradigm appreciate that ecosystems in a degenerative cycle continue to degrade. Think of drought, fire, flood cycles, heat waves. So I think we need to be a lot more proactive than the degrowth paradigm understands. And they don't understand the potential of a regrowth paradigm. That's something that we're thinking about. So regrowth is just a term that we've been thinking about and developing, very much related to the regenerative paradigm. It's partly about getting a really simplified message, a soundbite that people can easily share with other people. So emphasizing this point, the finite and infinite nature, or virtually infinite nature of fossil fuels are finite, renewables are relying on finite minerals, and we sort of pointed out some of the limitations that we need to think about. And a regrowth paradigm is about self-replicating life. And in the lifespan of each of these, we're talking about decades and hundreds of years. In a regrowth paradigm, depending on our stewardship, we're talking about the lifespan of the sun. So there's incredible longevity there if we're focusing on regrowth. So water is a key aspect of regrowth and regeneration. It's unique in that it doesn't disappear in our current atmospheric composition. It changes phases and it changes locations. We currently have a warming atmosphere that holds more moisture in a positive feedback loop. And how we steward the land determines how ocean moisture and atmospheric moisture can participate in the large and small water cycles. So it's an understanding that many in the mainstream don't understand. We've got brittle landscapes lacking water, and many landscapes that would benefit from more productivity. Like Will was saying, carbon projects don't work without water. So we need to rehydrate. Rock Dolman talks about slow it, sink it, spread it, store it, and share it. He's a fantastic permaculturalist. A lot of rehydration is super simple stuff. What we're doing is also very simple stuff, but it's just a little bit different. So I'll show you an animation shortly on how we bring a different aspect to what's already done. So there's an aspect of timing, and that can be aerobic timing, pumping for later gravity irrigation, and energy creation. So this is a video. Can everyone hear that all right?
How can deserts be transformed rapidly into rainforest? Deserts have rare rain events and can experience extreme runoff when it finally does rain. Evaporation is very high. We can capture extreme rain runoff in long swales and store it in a dam. We can then release the water to a fuelless pump that pumps water to higher water storage. The pump is powered by water. A percentage is pumped and the majority is discharged. The pump can be turned on and off the high flow, unpowered evaporation activated valve. This means that the discharged pump water is never too much for the soil or plants. The valve doesn't need electricity, internet, or Wi-Fi. It is a reliable low-tech innovation, making it ideal for remote sites and tough conditions. The pump is self-regulating and self-priming. By providing regular moisture at appropriate rates over large areas, plus fuelless pumping, we can rehydrate and regenerate deserts. We can increase infiltration time by 100. This means pioneer plant species can start growing and soil can be improved. The rapid improved water cycle will help regenerate at the fastest rate possible. This enables supercharged plant succession. Rapid recharge of groundwater with rain improves groundwater quality and raises the water table of the surrounding area. Fresh water is less dense and sits on top of the poor quality water. Trees and vegetation can also regulate the water table and salinity. The best place to store water, store carbon, and grow food is in the soil.
So that's an example of a strategy called maximum infiltration. We see a variety of other applications, all revolving around the same unpowered tech that have exciting multiplying and compounding effects as well. For example, infiltrating and pumping snowmelt. There's a particular setup you can use that can, in some places, double usable water. Fuelless pumped hydro storage is interesting. It's already got the best energy return on energy invested of renewable energy storage. If you can do that in a way with a fuelless water pump and enhance your water cycle of that local area and improve reliability, it becomes even more interesting. You can move water around on site. That's creates new possibilities there. There may be orographic effects with certain features where you get a moisture condensing effect that enhances. And I'm keen to go into these more in depth in a longer presentation. It'd be great sometime in the future. But another interesting one is a water relay that instead of discharging the water into the landscape, you're keeping it contained in concrete structures. You can have a whole lot of pumps in series, and the discharge water, which is the majority of the water through the pump, can be used multiple times. So 10 pumps in series, you can use the discharge water 9 times. You can also add water at any point to these water relays, and you can take water out, say for bore well recharge. You may be on a site with a lot of high evaporation and you want to replenish the groundwater and raise it and the water quality rather than have it sitting on the landscape where the wind will take it away. We often hear of scarcity versus abundance mindset, and it sounds a bit like hippie BS a lot of the time. But I think this is a demonstration of how stewarding the land for how much can I give instead of exploit the water resources has these improves, de-risks productivity systems, improves profit margin, improves productivity. So if you've got an exploitative mindset, you can think of it as having a credit account where you've got no intention of paying back. You're not investing in the land. A debit account is having the low-tech erosion control and replenishing what you're going to get out of the productivity. And we see our unpowered tech as like having a savings account with a 1,000% interest rate, because you're giving soils capability that they don't normally have. And then you get gravity irrigation or other applications as well. So we think there's potential for a regrowth era where this unpowered tech has really exciting applications for hyper-abundant productive systems, new expressions of ecosystems. There is no peak in ecological function where conditions for life are given. Nature will express and self-replicate to those new conditions. So that's what really excites us, that there's possibilities of amazing biodiversity and abundance. There's climate moderation, both in warmth and cool in regenerated ecosystems. And you could optimize the certain moisture and water cycle on site to benefit key endangered species as well, which may be attractive to people. And I hope that the key takeaways that you guys take away is that unpowered technology is a really good combination with powerful technology tools that you guys are all experts in, or many of you. So it's anti-fragile, it's decentralized, there's a strong independence and autonomy for local communities. And yeah, I think there's really exciting potential here. So thanks very much, and hope you can join the longer presentation, date to be determined. But yeah, I'd love to unpack this and unpack development so far. Thank you.
Amazing. Yeah, again, another individual in whom I will have plenty of questions for as we get into that section here in a bit. Michelle, on to you.
All right. Who can share? Oh, wrong button. I also prepared a few little slides for you guys. I am wondering though, a little bit about my audience. I did prep a few slides just to talk about, how does that show up? Just to talk a little bit about, I think often, tapping into what Will was saying, I think there is this idea that on our own properties, on our own little micro scale, the actions we take don't have an impact. There's this little bit of a concern that, oh yeah, I can put in a rainwater tank, or I can put in a mulched basin and it'll benefit me in my own property, but that, like, hey, the benefits get kind of muted at the larger watershed level. And so I did prep a few slides to just completely bust that myth, because I think that's can, with some audiences, be a really great place to start. Having said that, I also know that, you know, Steve and Will and Cody and who's our fifth participant here? Al. I don't know so much about your background, but I might be preaching to the converted here to talk to you guys about like all the reasons we should like think global but act local. And I can jump straight into some key tips for designing a rainwater harvesting tank, like things that you can actually take away from this presentation. So I would love, just before I get started, I don't have a lot of slides, just a quick poll. Do you guys want me to talk about some of the science and the systems science behind why small scale actions have big impact? Or, you know, skip that and jump straight into, hey, some tips for if you actually want to put in a rainwater tank, here's what you can take away. So yeah, you can unmute yourself. Just tell me, what do you guys want me to do? Where do
You
you want me to
share
go?
like the systems PowerPoint, but then let's talk about tips.
Okay, I'll try and get through it all. Okay, so let's talk a little bit about systems. Yeah, I find this stuff particularly fascinating, and it's kind of the why, right? Often. So this diagram here, hopefully you guys can see the whole thing. It represents a typical city or municipal watershed and water distribution network. So up here often is the case with cities or municipalities. We have this water supply catchment. There's a river, sometimes it's ocean and desal, a dam. And water is pulled from the river or ocean, treated, then pumped up into this network through this network of distribution pipes. And I am talking, you know, kind of city scale and municipal scale. And I know, you know, Stephen and Will, you guys were talking rural scale, but you know, I want to go this way too, because so much of our population, so many people live in cities. This is a huge, you know, water resource use in cities is huge. And so there are households distributed throughout this network that are using this water that's being distributed by all this pipe network, this centralized supply network. And these houses are, you know, I'm going to talk about this hypothetical dot here, red, but they're all through these sub watersheds represented by A, B, C, D, E, F, and G in this giant urban catchment. And this little hypothetical house that I just pointed to, this red dot, it has a hydrograph at the property line shown. Whoops, sorry guys, changed the slide accidentally. It has this, this is called a hydrograph. And what this hydrograph shows is that during a rain event, when rain is falling, you have time on the x-axis, pardon me, and flow rate on the y-axis. So you can see at the beginning of the rain event, there's just a little bit of water flowing off the property. And over time, at some point in time, you'll hit a peak rate, and then the stormwater off the property will eventually slow down back to zero. And then if you go downstream, sorry guys, I said I started here, but I want to start at this house. If you go downstream and you hit the second house in the block, you have two hydrographs, like Animal Day, Will, like your dog was bugging you and my cat is bugging me, so pardon me. At the second house, you have both hydrographs that basically, here's the first one and here's the second one, and they add up and you get down to this subcatchment point somewhere at the end of the community where you've got a hydrograph that looks something like this. And as you see, as we go downstream, as the water travels down the catchment through the urban waterways, the individual property curves just add up cumulatively, and you have these larger and larger hydrographs until you get down to the bottom of the catchment where the cities will place their stormwater management or their wastewater treatment, right? And when engineers and city planners are designing their stormwater infrastructure and treatment equipment, they have to design for this peak flow right here. So the size, the cost of the systems here are all based on this peak flow. And so with this diagram overview, we can talk about how better water management, and I'm talking about, you know, what Steve, you said, slow it, store it, soak it, share it, all of these things. There's many different ways to do that. Obviously, I'm a big fan of storing it with rainwater tanks, but all of these things will have these same net benefits. And by both reducing our reliance on this centralized system and the supply upstream and downstream. did we miss anything in terms of ways you can reduce your consumption on centralized systems? There's rainwater tanks, storage, there's like mulch basins. I don't know, what else do you guys have that you could do at your own property that could either reduce your dependence on centralized water supply or reduce the stormwater or let's say reduce, but change the timeline that the stormwater discharges from your property. I'm just gonna stop here. You guys have any others? Just throw them out. This
So,
for me is right.
so,
Permaculture.
so that's like one way that I try to explain our objective is to like attenuate the hydrograph.
Exactly.
Yeah. Yeah. And then if you do it, like I think you can do it so that like they start to stack up on one another. And so you have some water from like the last rain that's still around by the time you get the next rain. And yeah, you can get to like a water surplus pretty quick, but it evaporates away so quickly.
Yeah, depending on your context too, your climate and your context. But you're absolutely right. And I like to talk about, I know hydrographs is a little bit technical, but it's a nice way to think about it because you'll see in the next slide how impactful all these tiny micro installations can have on the hydrograph way down here. But let's start, before we talk about the downstream impacts, let's start upstream right here because, you know, most of us, if we're not harvesting rain and utilizing rain, or maybe you might have a well pump, but even if you're pumping your own water from the ground, you're taking water from some centralized supply, right? And a reduction in water use from this centralized supply right here has cascading and compounding benefits than first, like more than first meets the eye. So first of all, it's just been shown the minute you start using rainwater or put in a rainwater tank, your behavior changes. Just the act of starting to capture and monitor the level in your tanks, you use less water. Like, interestingly enough, same with solar panels. It's the same principles actually apply. The same principles that I'm talking about with water, I could almost have the same conversation and be talking about energy and renewable energy supply and centralized energy. Hold that in your mind. But back to water, on top of that, a lot of cities have old and aging water supply networks and infrastructures. Sometimes these have been built over half a century ago. And I take the city of Montreal as a great example. It's notorious for leaking pipes in this distribution system. And it's been estimated that at least 50% of the water that's treated here and pumped here does not make it to a house out here. So the minute, if you reduce your usage at your house by 50 liters a day, just at one house, it's actually double that is the savings by the time you work it back to the pump at the dam, because 50% of the water that they were trying to deliver to you got lost in the network of pipes right before it even got there. And it's not that bad everywhere, but losses more than 20% are very common in many, many cities. And so the positive benefits for the utility, which we kind of forget that utilities are often publicly owned companies, like this is our tax money that's going into funding these utilities and these water supply companies. But these benefits quickly become significant with the ability to avoid or defer, whoops, keep hitting the wrong button, guys, sorry about that. With the ability to avoid or defer the costs associated with infrastructure. It's a big one. Like pumping, you don't have to increase pumping capacity. This water treatment is expensive, and these projects are in the millions of dollars. Never mind that reducing the demands up here at all these little houses has huge implications on like energy costs, pumping energy costs. There's a term called water G because we don't realize how much energy is embedded in the water we use, right? So using less or like pulling less water from these centralized water supply systems just has also has huge positive ecological and environmental benefits as well. So we've got that like reduction in infrastructure costs for the municipality. We've got the reduction in energy costs, and never mind all the ecological benefits to these rivers where we're pulling water from. And that's just upstream. And I'm going through this really quick. But when we start doing better water conservation and management at our own little properties up here in the watershed, we also get all these incredible downstream benefits. So that's what I want to talk about in the next slide, and back to the hydrograph. So here in this, here we have at the top of the catchment, again, our little hypothetical, this time permaculture property, right? And this permaculture property compared to the conventional property, its hydrograph looks like this blue line because water is falling on the roof, it's going into rain tanks. The overflow from the rain tanks are probably going into some sort of a swale or mulch basin or some sort of like retention system. And then really even the downspouts that used to go just straight to the storm sewer are being redirected to fruit trees or something, right? There's lots of vegetation. There's lots of different ways to increase retention of water. So that's why you see nothing for this amount of time. It doesn't really matter how much time this is. And then eventually when everything starts, when your soils are full of water and your tank's full of water and everything starts pouring over, you get you get back up to that peak flow. And where this gets really interesting is when you start going down the watershed and you see two hydrographs side by side. So this is the next property at the bottom of the catchment. And then here's the subcatchment. So now what you're actually seeing is this huge reduction, and it's compounding in the peak flow, right? It's the same volume of water, but the peak is much lower. And then by the time you get down to stormwater management here for the municipality or for the community or for the catchment, you're seeing this substantially lower peak flow. And again, with that, you can really see how harvesting water and all these other strategies at your little itsy bitsy property that they feel like I'm not doing anything, it really does mitigate local flooding. It supplements the capacity of drainage systems. It decreases transfers of contaminants into the waterways. It reduces erosion and sedimentation by reducing that peak, right? And it improves the quality of water in waterways. Never mind significantly positively impacting operating and capital costs associated with stormwater treatment and discharge infrastructure that often has to be built down here. So with that, like there's just my, as quick as I could get through it, pitch on why, think global but act local, and like what you do on your own property is important and has compounding and cascading benefits. And often we think that the solutions have to be big, right? That we need to come up with some huge new treatment down here that's ecological and powered by this giant solar system. And it's no, we need small scale distributed solutions. That's how we're going to solve this problem, right? So that was my why pitch. I'm going to give you some really quick tips if you want to go out and set up a rainwater tank. People overcomplicate rainwater harvesting, especially in North America. It's crazy. The fear over rainwater, I think, has been perpetuated and maybe blown out of proportion by the water utilities, like players with conflict of interest, and they make it seem like it's like poisonous water that falls from the sky, and that if you harvest it, you're gonna die. Like there really is this attempt to paint rainwater in that light. But no, rainwater is actually distilled water because it goes up into the clouds and it condenses. It falls. It might pick up a few things on its way down, but it's very clean, and it's probably the cleanest and safest water you have access to, right? And I'm not scared to say that at all. It's probably better than the stuff coming out of your tap from your municipal water supply. And it's certainly better than the stuff coming out of your groundwater well. So this will take me only 2 minutes to get through because it is that simple. But essentially you're going to have a gutter, a roof and a gutter. And people, the number one question I get about rainwater harvesting is about materials, or always about materials. The group of questions: should I use this material, and I should use that material, and what tank material should I use, and this and that. And I'll tell you this, materials have virtually no impact on your water quality if you design your system well. Virtually no impact, with the exception of toxic materials. Stay away from anything that's toxic. But a stainless steel tank, which is very expensive, will almost have like the similar water quality to a poly tank, as an example. So don't use toxic materials, and use common sense, right? And you'll be fine. You'll get water that is sufficient quality for irrigating plants, no problem, and likely even sufficient quality for drinking. The second most important element in your rainwater harvesting system should be this leaf diverter. I don't have a better picture of it, but really that's all it is. It's a screen at a 45 degree with another screen horizontal and it just keeps organics out of your tank. And that's the biggest principle to remember. Like, rainwater tanks should be low nutrient environments. You don't want leaves in there. You don't want dirt in there. You don't want trees in there, and you don't want rats in there. They should be. It should just hold rainwater. And the way you do that is you put screen, like this leaf diverter, and you put screens on the inlet of your tank, and screens on your overflows, any inlets and outlets. That's point number 3. And then the really exciting thing about rainwater tanks is they actually form natural biofilms on the inside of the tank and on the bottom of the tank. And these biofilms are really hungry in low nutrient environments. And they're just incredibly effective at like eating up organics and inorganics. And when I say inorganics, I mean like lead. Like if lead did get its way into your rainwater tank, these hungry biofilms will like basically eat it up. And they've done some incredible research showing that the amount of lead and organics and parasites, bacteria, I should say, in the sludge layer in the biofilms is 10,000 times higher. That in the water column. The water in here gets really clean very quickly. And so all you need to do is don't disturb your tank. Leave your biofilms alone. Let them do their work. Don't drain your tank. Don't clean it with chlorine. Fill it up with water, and make sure you draw your water from about 4 to 6 inches from the base of your tank. Right, and that's what's shown here. You don't want to draw it from the, too close to the sludge layer at the bottom here. 4 to 6 inches from the base is all you need. And then lastly, most rainwater harvesting systems are going to have a pump, unless you manage to set your elevations so that you can not need elevations. But this pump also, all pumps need filters. Be interesting. Maybe not the Bunyip pump, Steve, you can tell me, but most pumps, most positive displacement pumps and centrifugal pumps will need some sort of a filter to protect them from mechanical failure, right? And it's a 30 micron filter. They're usually integrated in the pump housing. So there's another filter here in the event that something made it through here and made it through here and made it through your bioreactor and got pulled in. It'll get caught in your pump filter. And lastly, if there's some sort of bacteria that made it through all of these interventions, pathogens especially hate sudden changes in pressure. So you're pumping it. It's another intervention that's going to increase the quality of your water. And then I didn't really show you bringing the water into the house, but I would put a ceramic filter on my drinking water tap if I brought this water into my house. And I would put a filter on my drinking water tap if I was drinking rainwater or city water or groundwater, and the filter would be the same. So this filter isn't special to rainwater. This is about wanting to have good quality drinking water no matter the water source. Anyways, that was a whirlwind, but I know, we had 3 speakers and we want to maybe have time for questions. So I think I'll leave it there.
Wow. I know I have lots of questions. I'm sure other people have questions as well. So I don't want to take up the spotlight for questions. Does anybody have any questions for either of the guest speakers, or maybe the speakers have questions for one another? I'm curious to kind of open the conversation up, and just let's dive in. You all should be able to unmute yourselves now.
Yeah, so whenever I first joined the call, somebody was talking about having rejuvenated a spring kind of up high on a ridge. Who was that? And yeah, where are we located? Where is it?
Well, that was me, Cody, and that was located in Alberta, just kind of near Bragg Creek on a quarter section.
Cool. Did you do anything to rejuvenate the spring? Like, what do you attribute the success?
So far, we haven't done a whole lot, to be honest. We basically built a fence around the creek because initially the cattle were getting in and mucking up the creek pretty good, and they were actually pulling it up further. So it was actually going to be spitting out of the neighbors at some point. So we ended up fencing it off, and just did some really simple kind of slow sink, just sort of some shovel ready, like we built some one rock dams and just kind of slowed the flow through the property. But ideally, we're going to be putting in a bunch more infrastructure in the days to come. I'm kind of more in that observation stage right now, just with the small things that we have done. But I'd love to eventually have some ponds cascading down through that terrain, but haven't quite got there yet. Just been a little too busy, to be honest.
I think excluding livestock is like a huge win, and that's one of my own. Like that's a battle that I fight a lot. Just like a lot of our rangeland has really large pastures, and so a creek flows through the pasture, and it's cost prohibitive to build fence around it. Not to mention, the cattleman's going to be pissed if you fence cattle out from the water, and so we need like an alternative water infrastructure, which I think the Bunyip is really interesting in that respect.
I have a question.
Ask it.
Go for it.
Okay, this I'm really interested on the urban, solutions, and Steve's and Michelle's presentation reminded me of recycling the water is definitely something that I'll tell you a little bit about my background, and you can see the solution that I'm trying to find is basically, growing as much food as possible in each property. And, and that means like, having a food forest, a food garden, not just on the backyard or front yard, but also in the roofs, in the walls. I'm designing living walls, green roofs. So it makes me think, like, for example, here in California, like if you want to have a store rainwater, I mean, you would have to have like a very deep, a huge tank or something, right? Because it doesn't rain for like 5 months or 6 months, right? So I'm wondering if for example, in Steve's system, right? Like, is it possible or like to recycle that water in a place that it doesn't rain for that long? For how long can you keep like kind of? So I'm trying to imagine a kind of like a river system, a micro river system in a property where you have like a very deep pond or something or tank, huge, and then you just keep recycling that water to irrigate the plants. But something tells me that you just can't keep recycling the same water for that long. I don't know. What do you guys say?
Well, I can give a little bit of input. There's a saying that goes along the lines of the best place to store water is in the soil. Second best place to store water is at higher elevation, so you can get gravity irrigation. And the third best is just open water storage, which is down a hill. So if you take that framework and try and work with that, you can't keep doing the same water over and over without going through the water cycle. On a larger scale, that is how it works. But yeah, there's certainly good applications. Like in the desert to rainforest one, I'm in the dry tropics and we have a decent wet season of, say, 4 months or so and about 8 months of dry. So not only are you getting that pumping and infiltrating element, but you're getting the mid-slope dam is going down and it's a shock absorbing event. You might get 200 mils, or last year we had 900 mils in a 5-day rain event. So it's not going to shock absorb that, but it will go a fair way in utilizing those big rainfall events, which I'd say California has similar flood drought. And the flood is a destructive force instead of a productive force. So probably the smaller setting, the less justified a bunyip pump is in the context that we're using it, because of the discharge water, which is the majority of the water.
So basically you're saying, it has to work in a larger system. It cannot be this same system. It cannot be used in a micro, like in a smaller area.
It can, but you might be pumping 10% of your water from a tank, the water that you're capturing, and just say you're wanting to put it uphill to another tank to utilize gravity irrigation or something, you might be looking at 10% and discharging 90%, which you could infiltrate into your ground. So in my view, there is no wasted water because you're infiltrating water and you're getting gravity irrigation. So there is applications, but the larger the site and the more extreme the runoff, the more exciting the results.
Okay. Yeah, I'm trying to think of like a, you know, I don't know, like a block in a city or something, like create a system like for a block, or I wonder if even that is too small.
Maybe,
Or
I'm not sure.
5 properties or something.
I mean, California's in a desperate situation, so any improvement, this is my generalization from where I am. I just see fires and things like that, but more groundwater is more moisture, is more fungi that's breaking down the fire fuel load. So there's a whole variety of benefits where it may be justified more in suburban California than a non-brittle climate that's a lot wetter.
Steve, it sounds like you're kind of alluding to that if you start to solve for some of the basic root problems like water, you start to solve for some of the greater problems that exist, the fire hazards, etc. I think that's something that like maybe doesn't get talked enough about, and it kind of expresses like VDAO's approach for bottom up solutions and really thinking going back to like systems thinking. Um, and yeah, so it's great to see that you're highlighting about that and kind of touching on that a bit.
Yeah. And equally, from a drought perspective, if you want soil that has structure, you need moisture for the soil to be active. If it's dry dirt, the water's just going to go straight off the top. So regular moisture and ground being covered is important.
Yeah.
And within my own context, I've got some clay shale soils, and that can have a infiltration rate as low as 2 mil an hour. But if it's covered and regularly irrigated, that can be hundreds of mil an hour. So the potential is very exciting, even without unpowered technology improving things.
We've got some micaceous shale soils at the Wildcat property, and yeah, like it's incredible how much water it can hang on to. It's really cool.
You kind of cut off there on the end, Will. Maybe you could repeat the last couple sentences there.
I just so we've got some of these micaceous shale soils that they're just when they're in good shape they can hold a whole lot of water. I mean it's awesome, but when they're degraded you can't get them to infiltrate water. It just runs off the top.
Yeah, there was something that I've been learning and never really had thought about it until recently, is that there's a huge difference between dirt and soil. And that never really dawned on me. I kind of, I go outside, I look at the ground and there's dirt, and I don't think about how much depth there is to the soil, what's the quality of the soil, and how that might relate to the water, and it all is together, but yeah, I never thought, it ever crossed my mind until recently, and it just changed my whole perspective in the way that I think about things. But yeah, Michelle, I got a question for you. Sorry, I really am curious about rainwater harvesting. And so, are there like tools that somebody could have access to get an idea of how much they can expect to capture with their roof size, and then plan accordingly to how big of a capture tank they should have?
Yeah, and then there's great tools, and I built one to do that because often if you look out in you look for advice on how to do that, and even from ARCSA, the American Society of Rainwater Harvesting, I think they're called. They'll recommend like you take your monthly averages, you take your monthly average every month for rain, and then you take your average for your monthly usage for water every month, and you kind of finding your rainfall rates is pretty easy. Actually, we've never had better access to data. I remember when I started this project 10 years ago, it was really, really hard to get rainfall data. And we had to hire somebody on Upwork to like pull data from government websites. And nowadays I mean, just type in rainfall data. The US Center for Data, I think, makes data available across the world. You can get it. NOAA, yes, thank you, Al. And there's a really good one in Canada as well, but I think in Australia. But I'll tell you this, most places, if you ask that question, they'll tell you to use monthly averages. But if you think about it, like we experience rain instantaneously and we use rain instantaneously. Like, I don't care when I go to take a shower, I don't really care what the monthly average was. I want to know, like, did it rain? Yes, today. I want to use rain today. So those models are kind of shit, and they actually tend to underestimate by as much as 20% how much rain you can capture, which is kind of counterintuitive, right? The averaging effect makes it feel like you're not going to capture as and be able to utilize as much rain as you actually can, because rainwater works on small events. So when you're storing rain in a tank, it doesn't actually take a lot of rain on your roof to fill your tank, because the math is just the whole area times the volume of rain, and quite a bit falls. And most times, you know, you're never going to have a tank big enough that doesn't overflow on every single rain event. You're only holding back a small portion of the rain that comes. So yes, there's a tool. It uses daily rainfall data over the course of the past 30 years and models different tank sizes based on daily rain. There's 11,000 rows of data in this Excel spreadsheet is what it is. And so, yes, I have a tool, I use it, and that's what I do all my tank sizing and modeling on. It's a little bit too advanced to just hand it out to people. I don't even sell it because I don't want to have to show people how to use it. We teach people how to use it in the course we do on rainwater harvesting, and we give it out when you take a course. And honestly, the reason for that is just because I just don't want to deal with support on the tool, because it's an Excel spreadsheet, and we've talked about maybe turning it into a cloud-based tool that does the compute for you. But yeah, know this, for most people will say it never rains here, but if you actually plug it into the tool, you actually can collect and harvest quite a substantial amount of rain, quite a surprising amount of rain, I should say. Substantial, it always depends on your climate. So you might be surprised.
Awesome. Yeah, that's absolutely fascinating. If I remember right, I heard it was maybe you who had mentioned that the blue where the barrels that most people use are not, you'll basically just fill them up incredibly quickly. Like it'll take one rain event and you'll have filled them up, and it's almost you're gonna wish you would have done a bigger system.
Yeah, I think I tend to, a 5,000 liter tank is a decent number for a decent number of people. I mean, of course, it's hard to just throw out one number because there's different climates all over the world and different people using different amount of waters. But if you force me to throw out one number, so you could do some pricing and say, if I didn't want to do a lot of effort and just put in a tank that would make me pretty happy, I'd say go with a 5,000 liter tank. What is that in gallons? 1,300 and a bit US gallons. Someone should check my math on that. I don't have no idea if that's right.
What was it? 5,000 milliliter?
5,000 liters. Yeah,
5,000
milliliters.
Yeah, milliliters. Milliliters will be a little too small. 5,000.
Yeah. The cost. Someone asked, what's the cost to create a rainwater harvesting system? The tank's going to be your most expensive component, and that's why if you're putting in a big system, it's well worth doing the modeling to optimize your tank size. And think of it this way. Yeah, 13. Oh, I was close. Yay, Cody. Think of this: a well-designed system. If you had a tank, okay, you have three scenarios. You put in a tank, and the tank is always full, or the tank is always empty, or the tank is constantly increasing and decreasing in volume. Which of those three scenarios means that you've designed a really well system and you've optimized your costs for the size of your tank? What is it? We don't want your tank always empty, right? Well, we'll just help you with one of the two, because then you never have any water to use. If your tank's always full, what is that telling you? Your tank's too small, right? You got too much rain coming in. The tank's always full. It's always full. Even if you use it, more rain's coming in. So what you're really trying to get, if you're trying to cost optimize, is you're trying to see your volumes. You know, it rains, it fills up, you use it, it comes down. It rains, it fills up, or like by the time you use it, the next rainfall is coming. And so that's a good design. Increase and decrease, yeah, exactly. So cost wise, a 5,000 liter tank probably going to cost you a couple $1,000, and pump probably $500 to buy a good one, buy a good pump, and then all your fittings and so on and so forth. So quite a bit less than possibly installing, putting in a groundwater, like a well, but not insignificant for sure for water supply.
Awesome. Lots of great
Oh,
information.
yeah, I want to throw something else in. And again, resist the temptation to put RO, UV, chlorine, all of these black box end of line solutions. They won't work anyways if you don't put in good design up front. If you don't design your leaf diverter, and you keep all the nutrient out of your tank, and you draw from 4 inches above. If you don't do those things, those systems, those expensive, energy expensive and capital expensive systems won't work. And then if you do those things, if you do good design, you don't need them. You actually get good enough. You actually get like super high quality water. Because remember, we're starting with distilled water. We're starting with like your rainwater input into a roof harvested. I'm not talking stormwater harvested. I'm talking roof harvested rain system, right? You're capturing water off your roof. It's relatively clean. It's very clean to start, compared to, say, trying to drink water out of the ground, or drink water out of a ditch, or even drink water out of the river. They're different water inputs. That's why I can so confidently say that you don't need RO, and you don't need chlorine, and you don't need UV.
That's
Hey,
amazing.
Michelle, real quick.
Mhm.
Can I ask one real quick, or are you?
Yeah, and actually, you know what? Rob took the kids to soccer, so I'm good.
Sorry,
Yeah.
I don't know if I interrupted you there, Ben.
Go ahead.
I was just gonna ask, kind of like going back to my previous question and related to Ben's, like how big, like let's say, the issue, and like it doesn't rain for 4 or 5 months, so I'm thinking of a massive tank, like for how long can that water stay there? Can I mean, yeah, what's the longest that I can keep that water there and keep using it?
I guess it depends on your use. I mean, what tends to happen, right, when you start really getting serious about water and realizing you want a more resilient water supply, is you tend to start auditing your water use and realizing that the first place you need to start is in reducing your consumption, right? It'll be a lot cheaper for you to be more water efficient than to put in a bigger and bigger tank to try and meet your current needs. And serious rainwater harvesters, like Brad Lancaster in Arizona, he's fully on rainwater. He's got a couple really good books on rainwater harvesting. He lives in Arizona and has like fully on rainwater harvesting. No municipal water, no groundwater. But yeah, he has a composting toilet. You better bet, right? He's not flushing really great water down the toilet with feces. He's thinking that's too valuable of a use for rainwater.
Well, I'm thinking, food, a garden, right? Like for irrigation. That's why, there shouldn't be a limit.
Yeah.
So
but then
that's why I'm thinking, like, if you can,
yeah.
For how long?
So,
That's my question.
yeah, I can't really answer that, but I mean, the model the rainwater harvesting model, you can get your data from 30 years, and you'd have to have an idea of what kind of volumes you need to irrigate. But even that's tricky, because like Steve was saying, Stephen, maybe actually, pardon me, how much you need to irrigate depends on there's ways to reduce your irrigation too, by increasing your carbon content of your soil, right? So it kind of starts with healthy soils and adding compost and designing your garden to use as little water as possible as well. So you have to stack all these strategies together really at the end of the day. And it's really hard for me just to throw out a number that works for you without, you know, a little bit more context in terms of, you know, looking at the rain without me diving into it, grabbing rainfall data and really understanding your property. But yeah, I mean, there's no easy answers, unfortunately. I don't know if there are really easy answers. But we can't keep doing things the way we've been doing them.
Can I add one bit
Please.
to mulch? I think Michelle might correct me on this, but I think it's something like using 20 times less water when you're using mulch in the garden. Does that
Yeah.
sound about right?
Yeah, I believe so. Yeah. Yeah. Mulch
Yep.
can reduce your irrigation use.
Crazy.
So yeah, you got to do all those things
Um,
first and then try and meet your water budget. But you know, here's a very sobering exercise. Um, you're in US customary. So take um take all the areas of your roof. Like you can do this in Google Earth Pro. Um, look at the the plan view looking down at your house, and you can use Google Earth Pro to kind of figure out the areas of all your roofs. And you might have a house and a garage, and maybe you can harvest your neighbor's roof too, and get your area in feet squared or meters squared. I prefer metric because the equations are so much simpler, right? And then multiply that number in metric. Just do a quick Google search, like annual rainfall for my city, and you'll get a number in metric, you'll get a number in millimeters per year, and in metric, you'll get inches per year. And then the math is simple. To convert that, so if you hypothetically could capture every single liter of water that fell on your roof, you do the area of your roof in liters. I'll give you the US customary in a second. Area of roof in liters times the millimeters per year, and the millimeters and meter square cross out and actually gives you liters per year. So it's really nice. And then you think that's the maximum. That's the maximum I could harvest off my roof in tanks. And it'll be a lot, but it'll actually be sobering if you go through the math and figure out how much you use in your own home and how much you might want to use in your garden. And you'll probably be in a water deficit. You know, that is a big challenge. You know, trying to get within our water budget. And the equation for US customary is there's a conversion unit. Let me look it up and I'll paste it in the chat because I don't have it memorized. Un momento. And I'll pass it on to someone else. Yeah, actually, I'm looking at Cody in the message in the chat saying using drip and spray head irrigation. Yeah, yeah, you guys have lots of water. Great strategies. So I'll post the equations in the there you go.
While Michelle's digging for that, I had a question for you, Steve. Just in regards to those pumps that you showed, I was kind of trying to squint to see my tiny little window on my laptop here, but I was curious if one of those is related to like a ram pump, or if I was just maybe not seeing ram pump on there, or if there's one that's similar to a ram pump. I've always been fascinated by ram pumps, or I guess they're sometimes called hammer pumps. I don't know if they're similar in your area, but I didn't see that on that list. I'm just curious if you could speak to that maybe a little bit.
Yep. Similar principle. The Bunyip pump is a perpetual piston pump. So it's got an inflating tire and springs that draw it back down.
Right.
It's got a lot more capability than a ram pump. It lasts a lot longer. A ram pump has a hammer effect and they tend to self-destruct. If you want to pump a lot of water up to a certain rig. So the Bunyip pump's a lot lighter, lasts a lot longer, can be serviced by the pump owner, and it can pump to 750 meters elevation, one of the particular sizes. So that's pretty epic. That's 1,000 PSI. So there's all sorts of different flow rates, the fall that powers the pump, lots of different factors within there, but far superior to the ram, in my view.
Do you need a fair amount of head pressure to run that, or is it? Yeah.
minimum of 30 centimeters, but they're working
Okay.
on a pump that requires no fall, only flow rate. So that's a
Amazing.
prototype at the moment. Yeah, really cool. There's a big rig as well, which they've designed but they haven't built yet, and have an input of 150 liters a second, and can pump to 1 million liters to 50 meters head a day with about 10 million liters through the pump. So yeah, that's on a big scale, but some of the smaller ones are really impressive as well.
Yeah,
And
fascinating.
so it's a really cool pump. It's also self-regulating and self-priming. So it can adjust to various flow rates. It can start and stop itself. Some other RAM pumps have self-starting features. Well, a pupper pump does, but it's really complex. The Bunyip pump's really simple. Yeah, and so it's a really cool pump by itself, and we're utilizing that characteristic of starting and stopping itself, and then where it has been stopped with a float valve previously, and then our evaporation activated float valve is another float valve in series. So it can be made from off-the-shelf parts, and there's 2 points that can stop the pump. Rain comes again, flow starts again, and it'll start itself. So with the evaporation activated valve, if it's raining on site, the pump stops because you don't want to waterlog your trees and soil. When conditions on site determine that it would be beneficial to pump again, the pump will start again itself. So yeah, it's a great pump, and the applications that we see in various ways, they're really exciting as well.
Amazing. Thanks for that. That's a very great detailed answer. I just dropped the link in the chat. Is that an appropriate
Yeah,
link
that's cool.
for that pump?
It is, yep.
That's what you're
And
referring to? Okay.
hoping to do a longer presentation shortly to unpack all these things and tell you where our development is so far and get into more detail.
Awesome. Thank you, Steve. I will be tuning into that if I can.
Thank you.
Great. Michelle, you brought something up about using gray water for irrigation. And so is that like a form of a fully closed loop system then, of sorts?
Well, in nature, there's no waste. Only in human nature that we, you know, um, discard. Yeah. So yeah, I mean, it's systems thinking, right, on our own properties and starting to think more strategic. Like, if we're going to get to the point where we're living within our water budget, the only way we're going to do it is if we start applying more systems thinking to how we design our homes, right? And yeah, I mean, you think about the hand basin where we wash our hands and take our showers. It is kind of insane that the way homes are designed right now, that water is considered just waste, right? Just goes into the city, sewage, goes straight to sewage, when that's actually pretty clean water, and maybe it's a little dirty, but plants would love it, right? If we didn't mix it with sewage. So there's a lot of those things. A lot of times, a lot of us are stuck with homes that we bought that are already set up a certain way and are a little bit hard to retrofit, which is unfortunate, but that is the kind of thinking we need to get towards, for sure.
Interesting. And I
Mhm.
just want to be aware
Oh,
of
yeah.
time.
Yeah.
But just a follow-up question. Is it like what are some of the costs that are associated, or maybe it's difficult to give a general estimate, but how would somebody be able to retrofit, say, their shower and sink water to go into a catchment system that could then be used for irrigation for watering plants and garden?
Oh, it's not terribly expensive. I mean, if you live in a climate that has freezes in the wintertime, you have some considerations. Um, but I mean, it really just depends. Where people get tripped up in North America is regulation, actually, unfortunately. And yeah, that's just that's a whole nother area of work that needs to be done, is getting regulators on board with some of these things, right? Yeah. So we did it in Calgary. We redirected our shower and kitchen sink into our garden. It's really easy. Just a three-way valve. We did it ourselves. But then Rob started YouTubing about it, and we got a letter from the city saying we had to take it out. Well, maybe don't make a YouTube video about it. You'll be fine.
Words of wisdom. If you're gonna use your sink water, shower water, don't make a video about it.
Yeah. And of course, like, don't put your toilet water in your garden. Right? Okay, send that one to the sewage, right? Like, use your common sense. I think it's just so sad that some of these regs are just designed for the lowest common denominator. Like, people aren't allowed to use their common sense anymore, right? Yeah. And then Al, I saw you say like use rainwater for irrigation. Um, I mean, I would use stormwater and gray water for irrigation. Like, and personally, I think rainwater is the highest quality water first and foremost. So I would use it for my highest quality use, which would be drinking in my case. So my rainwater is reserved first and foremost for drinking and washing hands and bringing it into the house. And then the gray water goes to irrigation. And then it depends on your landscape. Stormwater is great for irrigation, right? So the water you might get from ditches or the water you might get from your neighbor's downspout or something like that. That's really good for irrigation. Or overflow water from your rain tank is good for irrigation. But it's my highest quality water. Yeah.
Amazing. So I know we're running a little over time, about 20 minutes over time actually. But you know, the conversation has been just really good. Lots of good information coming through. I just want to, you know, first of all, say thank you to the speakers today, Steve, Michelle, and Will. You know, it's been a really great discussion on water, everything water, really. And
And if you want to learn more, Verge's YouTube channel has tons of talks on free stuff on how to design rainwater harvesting systems that go into way more detail. And then of course we have courses on the website. So depending on what you're looking for. Yeah.
awesome. And
Don't put
Steve,
curb cutting.
and Steve, where can people learn more about what you're doing and stuff?
Sorry. We do have a basic website. We do a little bit on LinkedIn with, I've got two other co-founders. So we do regular Substacks on ecosystem design and things like that. So water cycles, it's fantastic. I think a key resource will be the next presentation I do here. That'll be one of the most comprehensive, putting all the pieces together. So please join that.
Yeah, definitely looking forward to that. We'll have to do a lunch and learn with you and really dive into that. And Will, what about you? Where can people see what you're doing with the Wildcat Bluff and your own land out there in those?
Yeah. I hate to say Twitter, but it's Twitter, Ogallala Live, at Ogallala Live, and then our website, and that is www.ogallala.life. Yeah, and we're up here, we're looking for arrowheads because like it's totally bare soil. And so like what you don't want is that. And whenever it rains, it just comes off. Anyway, you want soil cover and you want life. Thank you for having me. And I am sorry about the wind.
No worries. You're like I said, your mic right now is coming in like crystal clear. No noise at all. So absolutely fantastic to have you all here. If you want to learn more, you know, join VDAO, join the community on Discord, follow our YouTube, subscribe to the YouTube, and follow us on Twitter. Follow all these individuals here. Stay connected, and just get involved. Just really excited for the future. Thank you all.